Hi, today I'm going to be walking you through my process for the final design project. My student number is 400302853, and in this project I'm going to be designing some sequential logic to cycle through this number. I can start by making a state transition table and fill this in using the excitation table for J not K flip-flops. I'll talk a little bit more about how I chose the counter states later in my optimization, but the purpose of having these counter states is to differentiate between my repeated digits. So as you can see, 0 is repeated 3 times, and that's why I need the counter states to make sure that each state I'm cycling through is unique. From this table, I can set a lot of my inputs trivially, either to ground or to other outputs, and then I can find my non-trivial inputs using K-mapping. So here I've gone through the sum of products K-mapping for J1, 2, 3, and 4, using the logic that we learned earlier. So some methods that I took to optimize this design was first by simplification. For my J3, I can see here that I can simplify this expression a lot using an XOR gate from 8, and this takes it from 8 gates to 3 gates. Another method of optimization was checking the sum of products or product of sums logic statements using K-mapping. And when I did this, I found that in some cases it was the exact same amount of gates, where mostly in the other ones it was actually more gates, and this confirms that my original sum of products logic was the optimal choice. My last method of optimization was by setting my counter states. So initially, I had only set the counter states for the variables that repeated. However, I encountered a problem where my circuit was running through an external stable loop. To fix this, I set the states where it was going wrong, and I did this in a strategic way such that I could set more of my inputs to trivial logic. And I did this by trial and error, looking at what the output was going to be and trying to make the most optimized choices. Before I did this, I had to do logic gates for JC2, and this took 3 gates, but after I did this counter state optimization, that eliminated those 3 gates. So in all these design alternatives, I eventually condensed it down to using only 11 gates. This takes 2 AND chips, 1 OR chip, and 1 XOR chip. So now building it in Multisim, I started by laying out all my flip-flops. I connected up the clock signals. I hardwired the presets that I don't need for my first state, and hardwired the presets and clears to a digital interactive constant for those that I do need to set my starting state. And then I wired up all of my trivial inputs and used the logic gates here for J1, 2, 3, and 4. So now I'm going to be running through my student number in my Multisim simulation. So you can see I have my reset wiring up here in green to this digital interactive constant. So when I click space, that will activate those presets and clears. I'm going to press play, and we should see we're at my starting number, which is 4. So then I will press space again, and we'll see it run through this. 4, 0, 0, 3, 0, 2, 8, 5, 3. And there we go. I can then produce a timing diagram on Multisim. And as you can see, this is running through the exact states that we had expected properly. And now I'll explain the physical build. My clock signal is on the left. I have my 3 flip-flops and my decoder chip on the top, and I have my 4 logic gates on the bottom. I hardwired them to power and ground. I have my presets for the ones that I don't need in my starting state hardwired, and I have the ones that I do need in my starting state using pull-down resistors. So I can tap these to ground to set my starting state. And so now I'm in my starting state of 4. And then when I turn the function generator on, we should see it cycle through my student number. 4, 0, 0, 3, 0, 2, 8, 5, 3. After seeing the physical build, these diagrams that I produced may be better in helping to visualize what's actually going on in the logic. But regardless, we saw that this circuit runs through my student number correctly in both Multisim and the physical build. This lab really helped me gain a better understanding of digital circuits and how computers work. And this course as a whole really helped me gain better knowledge of analog and digital circuits as a whole. I have much more knowledge now than I did at the beginning of the year, and I think my largest takeaway from this course, and is specifically shown in this lab, was troubleshooting and algorithmic problem solving. I think this has been a super valuable course. Thanks for listening.